Okay, so this is the third part of the video for waves. Okay, so I hope you have watched the first two other video in order to help you do your tutorial. Okay, so let's start. Okay, so we learned that we learned about this formula V equals to F lambda. Okay, that means using the frequency of the wave and the wavelength of the wave, we are able to find the speed of the wave. Okay, this was covered in the second video. However, this is based on if the wave is passing through a medium that is of a constant depth. Okay, but as a wave travel within a medium with different depths, okay, example your water waves, the wave speed V and the wavelength will change. Okay, so the wave speed and wavelength will change. What doesn't change is the frequency. Okay, the frequency stays the same. Please write this down. Okay, and I have summarized this in this segment here. I call it the SSSS. Okay, so we have 4 S's. Each one stands for different stuff. Okay, so the first thing that you need to remember is the frequency stays the same. So this is the first S, same frequency. Okay, why is it the same? Because the frequency can only be changed at the source of vibration. Okay, can only be changed at the source of vibration. So only when the source changes the frequency of vibration, then the wave that comes out of it will change its frequency. Otherwise, it will be constant. Okay, so same frequency, that's the first S. The second S is shallower. Okay, so S stands for shallower. So we are using a water waves as an example. So if the water actually changes depth, it becomes shallower. Okay, so this means that the water goes from deep to shallow. So this is the second S. So what happens if it's shallower depth? That means the speed will be slower. Okay, so same frequency. If the water wave goes from deep to shallower, the speed will slow down. So the water will slow down as it enters a shallower region of the medium. And based on V equals to F lambda, okay, the frequency remains the same. And if it goes to a shallower region, the wavelength will be, the speed will be slower. Speed will be slower. Okay, that means the wavelength will be shorter. Okay, so this is according to V equals to F lambda, right? So please remember this SSSS. So the first two things that you need to know is the frequency will remain the same. Okay, later on we'll see some questions that will actually trick you on this. But when does it change? When the depth changes. Okay, then it will trigger a slowdown in speed and shorter wavelength according to your SSSS. Now let's take a look at this example. Okay, the diagram shows a water wave in a ripple tank. The wave has a speed of 12 meters per second at R. So I'm going to annotate here 12 meters per second. And the water waves crosses a boundary PQ where the distance between successive crests, that means this is your wavelength, changes from 3 to 1.5. So as you can see from here, although not to scale, it is 3 and over here is 1.5. So we need to use our SSSS. So the first S is same frequency. Okay, so the frequency do not change. The information given here is that there's no talk about where is it shallower or where is it deeper, but they tell us that the wavelength actually decreases, so it becomes shorter. So if it's shorter wavelength, it means it must have entered a shallower region, right? That means the speed must be slower speed. Okay, so what's the velocity of the wave at point S? Now this is 12 meters per second, and since V equals to F lambda and the wavelength frequency doesn't change, so can I say that F at R equals to f at s, the frequency, right? That means if I were to make it the subject of the formula, f equals to v over lambda. That means v over r over lambda over r equals to v over s, vs over lambda s. Okay. So please rewind the video if you don't understand how I got Vr over lambda r equals to Vs over lambda s. Basically, the frequency remains the same, and if I were to use V equals f lambda and make f the subject of the formula, I would arrive at this. So what do we have? Vr, we have this value of 12. The wavelength is 3, so put in correctly. Vs is unknown. The wavelength is decreased from 3 to 1.5. Okay, so the answer Vs will be 6 meter per second. And did it show that the speed decreases? Yes. Okay, so D is confirmed out, A is confirmed out, but how do we see whether is it B or C? We have to use this formula and use the SSSS. Okay. Okay, next we go back to success criteria A because they want us to define the term wavefront. So this is a definition that you need to memorize. A wavefront is defined as an imaginary line on a wave that joins all adjacent points that are in phase. Still remember in phase? In phase means same velocity and same displacement. Right? The particles are at the same displacement and they have the same velocity. Okay, so we can make a planar wavefronts, that means straight wavefronts, okay, by using a straight dipper. Okay, or we can actually make a spherical or circular wavefront using a spherical dipper, or when you throw something into a pond, okay, it will actually repose out in a circular pattern. Okay. Now, this is important. The distance from one wavefront to the next wavefront is the wavelength. Okay, so this dotted line, imaginary lines, are actually your wavefronts. Okay, and they are actually at the crest. It forms at the crest. So if I were to draw a side view, so this is a side view of a wave. Okay, and another wave. So all these are actually the wavefronts. But why is it that we see the crest and not the trough? Why is it that we see the crest but not the trough? It's very simple, because the crest is actually the highest point. So the highest point, it is able to reflect light into our eyes much better. So it is more obvious. Whereas the trough is at the bottom, so it doesn't reflect that much light. Okay, because of course, those at the top, you will be able to receive more light from their reflection. Okay, that's why usually, or I would say, the wave fronts are actually crests. Okay, so meaning I use a line to join all the crests together. Okay, anyway, this is important. The distance from one wavefront to the next wavefront is the wavelength. Okay, so let's see how we can solve this question. A Ripple tank is used to create circular waves as shown in the diagram below. The dipper creates the waves at a frequency of 20 Hz, annotate F, and the speed is 20 cm per second, so this is V. Okay, what is the diameter of the largest circle X as shown in the diagram below? So to solve this kind of question, I need to teach you this. Count the gaps. Okay, not the lines. What do I mean by that? The lines are actually your wavefronts. Okay, they are actually your wavefronts. Okay, and in between wavefront to wavefront is actually a wavelength. It's actually a wavelength. So we should count the gaps, meaning we are counting number of wavelength. Okay, the number of wavelength. So if this is the center, okay, I count that there's 1, 2, 3, 4, and 5. There are actually 5 gaps from the center to X. That means there are 5 wavelengths. Okay, please do not count the lines, count the gaps. This is important. Okay, so we have this formula V equals to F lambda, and it's given that it is 20 cm per second equals to the frequency is 20 Hertz. So this is my wavelength. Take note, since the speed is in cm per second, later on the wavelength will be in cm. So it will be 20 divided by 20, 1.0. Okay, and now because there are actually 5 wavelengths, the diameter, which is 5 wavelength, is actually 5 cm. Okay, but they are asking for diameter, so this is only a radius, so the answer will be 10 cm, right? Okay, let's look at another example. A wave generator which makes 10 oscillations a second. 10 oscillations a second, this is actually my frequency. Okay, this is actually my frequency. So my F is 10 Hertz. So with that, I can actually choose C and D to be the answer. A and B is incorrect. Okay. Which of following shows the correct values of frequency, wavelength, and speed of the wave produced? So this is a wave generator. So I have a length of 12 cm. It is not a wavelength, right? Rather, we should count the gaps. Okay, let's count the gaps. I have 1, 2, 3, and 4. I have 4 gaps. 4 gaps, it means I have 4 wavelengths. Okay, and 4 wavelength has a value of 12 cm. That means 1 wavelength is actually 12 divided by 4 equals to 3 cm. So I have my wavelength ready. Okay, so answer should be C. But let us verify whether the wave speed is this. Use V equals to F lambda. The frequency is 10, the wavelength is 3, so I should get 30. So answer is C. Okay, let's look at A3. The diagram shows the change of direction experienced by water waves passing from one depth to another. Okay, so all these are the wave fronts. The lines are the wave fronts. Okay, and the gaps between wavefront to wavefront is known as the wavelength. So do you see that in X, the wavelength is larger than the wavelength in Y, which means that by using SSSS, Y is actually shallower. Okay, the waves in depth Y have, okay, so if Y is shallower, that means the speed is lower, right? SSSS. So it will be B. Lower velocity Y, because Y is shallower. Why? Because the wavelength in X for the waves is larger than the wavelength of the waves in Y. Okay, and then by using SSSS, we should be able to get the answer to be B. C and D confirm wrong because they say frequency actually changes, but frequency doesn't change. As the waves goes out already, okay, they appear, the frequency cannot be changed. It can only be changed at the source. Okay, then let's look at A4. Waves travel more slowly on the surface of water when the water is shallow. So they tell us this thing, but it is good to memorize the SSSS. Okay, so let me say again, same frequency, that's the first S, shallower depth, slower speed, right, and shorter wavelength. Okay, so if it's shallower, the speed will be slower, the wavelength will be shorter. They all have the same frequency. Okay, so a girl makes an oscillatory motion by dipping her fingers up and down. The diagram shows the wavefront on the surface of the pool. Which one is the most shallow? So answer will be A. Most shallow, the wavelength is the shortest. Okay. Now, figure below shows circular wavefronts produced at the center of a circular ripple tank. Two corks A and B float on the water in a ripple tank. They move up and down the surface of the water as the wave passes. Okay, so this is cork A and this is cork B. Okay, the wavelength of the wave is 8 cm. So let us write this down. Wavelength is 8 cm. It's also shown here. Okay, so they give us a DT graph. Do you still remember what DT graph gives? It gives the displacement for the x-axis, sorry, for the y-axis, and it gives the period, which is actually the time taken to complete one wave in the x-axis. Okay, so figure below shows how the displacement of A varies with time. State the amplitude of the vibration of A as the wave passes. So amplitude is taken from the displacement. Okay, amplitude taken from displacement. So it's 2 that's unit 2.0 mm. The horizontal distance between A and B is half the wavelength of the wave. Okay, on the figure below, sketch a graph to show how the displacement of B varies with time. So this is for A, and B is actually 2 steps, right? 2 steps behind it. Do you still remember every time a particle complete one wave, okay, it will do 1 step, 2 step, 3 step, and 4 step. Okay, that means when A is here, B should be at the bottom. Okay, B should be at the bottom, right? Because B is in the center between 2 wavelengths. B is in the center of 2 wave fronts. And just now I told you wave front is actually the crest position. Okay, that means B will be in the trough position. Okay, so that means when A is, if let's say A is here, B should be here. So this is B. When A is here, okay, B should be here. Okay, so it will look like that. So you find that the waveform is actually opposite, right? That means when A is doing something, B is doing something opposite of what A is doing. So this is anti-phase, out of phase. Okay, but let's say this is A and I have another particle at C. Okay, they are both at the crest, so they are both in phase. But for B, because it is in between 2 wavefront, it is at the trough, so it will be doing things opposite of A. Okay, so determine the frequency of the wave, so we can actually get it from the x-axis to get period. So in order to complete one wave, let's take a look. I'm going to just erase this. Okay, if I look at A, how long does it take to complete one wave? Okay, so it started like that, it ends like that. Alright, so it takes 0.5 seconds. So period of A is 0.5 seconds. Okay, so how do we find the frequency? Frequency A is equals to 1 over period, right? So it's 1 over 0.5, so it is 2 Hertz. Okay, so this is C part 1. C part 2, the distance between the center of the ripple tank, which is this, and the edge is 40. Okay, determine the time taken by a wavefront to travel from the center to the edge. Okay, so actually, sorry, I made a mistake. It shouldn't be here. Okay, it should be 1, 2. Remember, one wavelength is 8 cm, right, as shown over here. So I have 1, 2, 3, 4, 5. So this is the edge of the tank, but it doesn't matter. So I have 1, 2, 3, 4, 5. 5 times 8 is 40. Okay, so determine the time taken to travel from the center to the edge. Now we can actually find out what is the speed. Speed of the wave is v equals to f lambda. We calculated the frequency. Frequency is 2 Hertz, right? The wavelength is actually 8 cm. So that will give me 16 cm per second. So if you're wondering how come the Hertz and cm would give rise to cm per second, don't forget Hertz is actually the unit for frequency, and frequency is 1 over period. So it is actually, I can write it as 2. The units is 1 over second. Okay, because it is inversely proportional. Okay, so that's why I can get 16 cm per second. Okay, the distance between center is 40, so calculate the time. Distance equals to speed times time. The distance is 40, the speed is 16, so the time will be 40 over 16, 2.5 seconds. Okay. Okay, so this is the last part of this video, so please watch it. I will be coming out with a video for the tutorial. Okay, I understand that I can only do until part 6 because we have not learned about sound. Some of you told me that it's compression and reflection, so I'll come out with a video soon. Okay.